Welcome. In this lecture, we're going to talk about another form of energy, potential energy. And specifically, we're going to talk about two different kinds of potential energy, gravitational potential and spring potential or elastic potential energy. And we talked about already one form of energy, kinetic energy. Moving objects have energy because when they hit something, they can do work on that object. And we defined energy then as the capacity to do work on an object. So anything that has the capacity to do work on an object has energy. So with potential energy, we can think of it as stored energy. It's energy that's stored in a system that under certain conditions, that stored energy can do work on an object. The first one we're going to look at, because we just got done talking about the work done by springs, is the energy stored in a spring. So let's say that this right here, x1, is the rest position of the spring. That's where the spring wants to stay and wants to be at when it's at rest. So this block has compressed the spring, and now the spring is just sitting there waiting. And you can feel the tension. The spring wants to release, and it wants to accelerate that block to the right. It wants to do work on the object. So since the compressed spring has the capacity to do work on the object, then it has energy. And it has what's called spring potential or elastic potential energy, because it is compressed past its or shorter than its rest position, or compressed some distance x1 minus 0 past its rest position. Also, you can get a spring that has potential energy when it's extended past its rest position. In that case, it wants to pull the object back towards the rest position instead of push it towards the rest position. All right, so either way, we've got elastic potential energy. So we abbreviate potential energy with a U, and we can say here spring, or we could say U for elastic. Both of these are the same, so spring or elastic potential energy. So let's look at the work that can be done on this box in going from this position 0 to this position x1. The work, as we've already talked about for a spring, is equal to 1/2 kx squared. In this case, the spring is going to be doing positive work on this block. And so since this spring is doing positive work on the block, it's speeding it up, we see that it has the capacity to do this much work, 1/2 kx squared on the block. X, again, being that compressed length from the rest position here to this position here. All right? So if a compressed spring with this compression x has the capacity to do this amount of work, then it has, when it is compressed, this amount of stored energy, 1/2 kx squared. So it's no mystery then that the spring potential energy here is given by the equation 1/2 kx squared. So the work equation and the spring potential energy equation look very similar. They are the same thing, as a matter of fact. Okay, so anytime we compress a spring by some distance x, then it has this much potential energy. And anytime we extend a spring by some distance x, it has the same potential energy. And we can also see that the spring potential energy depends on k, the spring constant. The bigger the spring constant, the more potential energy a spring will have for a given compression or extension. Okay? So that's spring potential energy. Let's take a look at another potential energy that caused by gravity. Okay, so let's talk about gravitational potential energy here. Here we've got a massive object that is some distance y, or some height y, above a table. And that table is also above the ground, or above the floor. And we're going to talk about the kind of energy that this object has because of gravity, because there's a force of gravity on it that makes it want to accelerate down towards the table. So if we draw a free body diagram for this mass, there is only mg going down, one force acting on it. So the net work done in taking this ball from that height y all the way to the table is going to be the work done by mg is equal to the force of gravity, mg, times the displacement, which in this case is going to be y, times the cosine of the angle when the force and the displacement are placed tail to tail. mg is pointing down, the displacement is also down, so this is actually the cosine of 0, which is 1 in this case. So we see that the work done by the gravitational force is just equal to mgy. So when this ball is sitting a distance y above the table, the gravitational force has the capacity to do work on this object. It is going to speed this object up on its way to the table. So again, if the ball essentially has the capacity to do work, then it has energy. And it's a stored energy. I can easily envision holding this ball up here at this height, and it's just sitting there. It wants to fall to the table. And if I'm holding it, it's not going to fall to the table, but the instant I let it go, boom, all of a sudden gravity can do work. So just being above a surface, then that object, because it has mass, because it has an attraction to the Earth, has stored energy. All right? And in this case, that stored energy can do exactly this much work in bringing it to the table and accelerating that object to the table. And so this then becomes our equation for what's called gravitational potential energy. U sub g is most commonly how it's written, and it's equal to the work that it has the capacity to do. So mgy. Now, y is special here, because what if I wanted to talk about the energy of the object because it's not some distance y above the table, but it's because it's some distance y1 above the ground? Then we can see that the ball here would have more gravitational potential energy because gravity is going to do more work on it. The displacement is over a longer distance. Same force, longer distance, more work is done. Okay, so y is really the height above some reference level. All right? And that reference level can be wherever the heck we want to put it. Okay, so if we're talking about the gravitational potential energy of this object because it's going to fall to the table, the most convenient place would be to make the table our reference level. That's where y equals 0. And then our height above the table is just going to be that distance y, the blue line right there. If we're talking about the ball falling to the ground potentially, then it would probably be most convenient to make this our 0 level. This is just like we did with something like projectile motion when we determined where the origin, y equals 0 and x equals 0 was, and we could do it anywhere we wanted. So usually we do it in the place that's going to make mathematically the most sense and make the problem the easiest. So let's make that specific here. It's the height above some reference level, and this is defined by you. You have the power to choose where that's going to be. Okay? So what we can see here with the gravitational potential energy, it depends on the mass of the object. So the bigger the ball, or the bigger the object, let's say this, the more massive the object is, the more gravitational potential energy it's got. It also depends on the height above the reference level. The higher you are above that, then the more energy there is. Now let's stop and take a second to talk about the units here. The unit for gravitational potential energy, because it is an energy, is going to be the same as the unit for kinetic energy, which is joules. All right, so the unit for you is joules. And we can confirm that here. Mass is given in kilograms, g is an acceleration, meters per second squared, and we're multiplying that times another distance. So m, so we got kilograms, meters squared over seconds squared. Hey, that's a joule. Going back to our spring potential energy, remember that the units for K were newtons per meter, and we're multiplying that by a meters squared. So we get newtons times meters, which again is kilograms meters squared over seconds squared, also the joule. All right, so that is our unit for potential energy, for kinetic energy, and for the work done. Now, what's most important here with gravitational potential energy, usually we're not just interested in the gravitational potential energy of an object right here. That doesn't provide us a ton of useful information. Usually what we're interested in is the change in the gravitational potential when an object moves from one position to another position. And really, one way or another way to look at potential energy is looking at it as energy of position. We talked about the fact that kinetic energy is energy of motion. Well, gravitational potential energy is kind of energy of position. Where this object is in reference to our y=0 point determines its potential energy, how much stored energy it has. The same with the spring. This distance right here, the delta x, determines the amount of potential energy that this block is going to have. So again, spring potential energy is kind of energy of position. All right, where are you in the system in which you're studying? So for this system right here, gravitational potential, the system would be the ball and the Earth. And we specify the Earth because without the Earth, there wouldn't be any gravitational potential energy. This ball wouldn't be attracted to anything. It wouldn't go anywhere if it was released from rest. So we talk about the ball-Earth system, gravitational potential energy. Here, we would talk about the spring mass system. All right, so what is the potential energy of the mass in this spring mass system? Depends on the spring, depends on what x is. Okay, so let's take a look at a couple examples here. And the first one we'll talk about gravitational potential and what the change in gravitational potential is. And we're going to see that our choosing of a reference level doesn't affect the outcome of finding the change in gravitational potential. All right, so same situation as last time. We've got a ball that is now a certain height h above the table. And let's say that the table is that same height h above the ground. And the ball is going to fall to the table and hit the table. And we want to know what is the change in the gravitational potential energy of the ball when it goes from its height h above the table down to the table. And the purpose of this is to show you that the choosing of the reference level is not going to affect the outcome of this problem. And let's do the problem first where the tabletop is y=0, which is the most logical choice for what this is going to be, or for what the reference level should be. So then we've got the gravitational potential energy is equal to mgy, where y is the height above the reference level. And in this case, and this is going to be, sorry, the initial gravitational potential. That would be mgh. The final gravitational potential, UGF, is going to be, again, mgy, where y is the height above the reference level. But in this case, the ball is at the reference level, so y is 0. So we get 0 for mgy when the ball is on the table. So then the change in our gravitational potential is going to be u final minus u initial, and we get mgh minus 0, which is just mgh. Let's do it instead for choosing our reference level at the ground, y=0 here. Then at the ground, we have the initial gravitational potential is going to be mgy. Again, y is the height above the reference level. This time, y is 2h. So it's mg times 2h. That's the initial gravitational potential. The final gravitational potential is equal to mgy again. And this time, the height above the reference level. The ball's at the table now. So the height above the reference level is h. So we've got mgh. And to find the change in the gravitational potential, delta u is equal to u final minus u initial. And we've got mg times 2h minus, oh, sorry. I did not do, that's the initial. Let's cross that out, delete it. It's mgh minus 2 mgh. And so we get negative mgh. We think, uh-oh, they didn't match. That's because I messed up here. This was not final minus initial that I did up here. I did initial minus final. Final was 0, initial was mgh, so we end up with a change in gravitational potential of negative mgh. So negative mgh, it doesn't matter. We could even, for grins and giggles, make our gravitational potential 0 level to be there. So if y is equal to 0 up there, then the ball starts with 0 gravitational potential, and it ends up with negative mgy. Finally, and you still do final minus initial, negative mgy minus initial, and this is negative mgh, minus 0 is equal to negative mgh. So it doesn't matter. pick it at the most convenient spot. Pick it at the spot that makes the most sense. If the ball's just going down to the table, I say make the reference level the table. Okay, that's it for this one. I'll see you next time.